13.8 billion light-years away in the direction of the constellation Virgo, there exists a supermassive black hole containing several million times the Sun's mass that appears to have formed when the universe was only a few 100 million years old. So early in cosmic history that standard black hole formation models cannot explain how it grew so massive so quickly. The James Webb Space Telescope has detected this and several similar behemoths, creating what some astronomers call the impossible early galaxy problem, and raising profound questions about whether our understanding of the Big Bang timeline, black hole formation, or fundamental cosmology requires revision. We thought we understood the cosmic timeline. The Big Bang occurred 13.8 billion years ago, creating space-time, matter, and energy in an initial hot, dense state. The universe expanded and cooled. The first stars formed after approximately 100 to 200 million years. These stars lived, died, and left behind stellar mass black holes of perhaps 10 to 100 solar masses. These black holes gradually accumulated mass through accretion and mergers over billions of years, eventually becoming the supermassive black holes of millions to billions of solar masses observed in galaxy centers today. We discovered something that challenges this orderly sequence. Webb's observations throughout 2023 and 2024 revealed quasars, extremely luminous objects powered by matter falling into supermassive black holes at redshifts exceeding Z(10), corresponding to when the universe was less than 500 million years old. These quasars show black hole masses reaching millions of solar masses, far larger than theoretical models predict could form in the available time through standard growth mechanisms starting from stellar mass seeds. The most striking example, a quasar designated UHZ1, shows characteristics suggesting its central black hole formed when the universe was approximately 470 million years old. Yet the black hole contains roughly 40 million solar masses, a mass that standard accretion theory says should require billions of years to accumulate, not a few hundred million. The black hole appears to have existed before sufficient time elapsed for it to grow to observed size through known processes. This creates an apparent paradox captured in the provocative claim that the black hole is older than the Big Bang. The phrasing is technically incorrect. Nothing can be older than the Big Bang, which represents the beginning of time itself. But the paradox is real. The black hole's properties imply it formed earlier in cosmic history than theoretical models allow. Either the black hole grew impossibly fast, or it formed through alternative mechanisms bypassing stellar evolution entirely, or our understanding of cosmic chronology contains fundamental errors. Dr. Priyamvada Natarajan, a theoretical astrophysicist at Yale University, whose research focuses on supermassive black hole formation, emphasized that these Webb discoveries represent genuinely puzzling phenomena that push against theoretical limits. The rapid appearance of such massive black holes suggests that either black holes can grow far faster than Eddington limited accretion allows, or that alternative formation channels, including direct collapse of massive gas clouds, create much larger seed black holes than stellar evolution produces, or that exotic physics, including primordial black holes from the very early universe, contributes to early black hole populations. This exploration will take us from the Big Bang timeline through the formation of the first stars and black holes, from Webb's observational capabilities detecting the universe's earliest quasars, to theoretical frameworks explaining black hole growth. We'll examine what age means for cosmic objects, how astronomers date distant phenomena, and what alternatives might resolve the paradox of impossibly massive early black holes. We'll discover that the solution likely involves not abandoning the Big Bang framework, but rather recognizing that black hole formation in the early universe involved more diverse and rapid processes than previously thought. If you're fascinated by discoveries that challenge our cosmic timeline and force reconsidering fundamental assumptions about structure formation, subscribe and give this video a thumbs up. And consider this: If supermassive black holes can form within a few 100 million years of the Big Bang, rather than requiring billions of years, what does that reveal about the exotic physics operating in the early universe, when conditions differed dramatically from today? Comment your thoughts. I'll pin the most insightful response. For most of astronomy's history, the universe's age and structure formation timeline remained unknown. Early 20th century observations revealed galaxies beyond the Milky Way and discovered the universe's expansion, but the exact age remained uncertain within factors of 2 or more. Different measurements of the Hubble constant, the expansion rate, produced ages ranging from roughly 10 to 20 billion years. The cosmic microwave background discovery in 1965 confirmed Big Bang predictions that the early universe was hot and dense, leaving thermal radiation filling space. Detailed measurements by satellites including COBE, WMAP and Planck refined cosmological parameters, ultimately constraining the universe's age to 13.797 plus 0.023 billion years. This precise chronology establishes a definite timeline for structure formation. The first stars, called population 3 stars, likely formed between 100 and 200 million years after the Big Bang, when primordial hydrogen and helium gas first collapsed into sufficiently dense clouds to ignite nuclear fusion. These massive stars lived briefly, perhaps only 2 to 5 million years, before exploding as supernovae and leaving behind stellar mass black holes. Standard models propose that supermassive black holes grew from these stellar mass seeds through 2 primary mechanisms: accretion of surrounding gas and mergers with other black holes. Both processes take time. Accretion is limited by radiation pressure from infalling matter, while mergers require black holes to find each other through gravitational dynamics in galaxy centers. The Eddington limit constrains how fast black holes can grow through accretion. When matter falls onto a black hole, friction heats the material to millions of degrees, creating intense radiation. This radiation pressure pushes against infalling matter. The Eddington luminosity represents the maximum luminosity where radiation pressure exactly balances gravitational attraction for spherically symmetric accretion. For a black hole accreting at the Eddington limit, the mass grows exponentially with e-folding time, the time to increase mass by factor e2.718 of approximately 45 million years, assuming 10% radiative efficiency. Starting from a 100 solar mass seed, reaching 1 million solar masses requires approximately 10 e-folding times, or 450 million years, of continuous Eddington limited accretion. Reaching 40 million solar masses demands even longer. Yet Webb observes black holes with tens of millions of solar masses existing when the universe was only 400 to 500 million years old. If these black holes formed from stellar mass seeds 100 to 200 million years after the Big Bang, only 200 to 400 million years remained for growth, insufficient time for standard Eddington limited accretion to produce observed masses. 3 major possibilities emerge to resolve this tension. First, black holes might grow faster than Eddington limits through super-Eddington accretion in special conditions where radiation pressure escapes preferentially along rotational axes, while equatorial inflow continues. Second, seed black holes might form much more massive than stellar remnants through direct collapse of massive gas clouds, creating 10,000 to 100,000 solar mass seeds that require less subsequent growth. Third, primordial black holes formed in the very early universe from density fluctuations might contribute to early black hole populations. Understanding which mechanisms operate requires examining Webb's observations in detail, exploring theoretical models for rapid black hole formation and growth, and considering how these discoveries fit within or challenge the standard Big Bang cosmological framework. The provocative claim of black holes older than the Big Bang serves as entry point to genuine scientific puzzles about the fastest, massive structure formation in cosmic history. Now let's begin by establishing the Big Bang timeline and cosmic chronology that creates the context, making early, supermassive black holes so puzzling. The Big Bang timeline. The Big Bang represents the beginning of space-time itself approximately 13.8 billion years ago, when the universe existed in an extremely hot, dense state and began expanding and cooling in a process continuing today. Understanding the cosmic timeline from the Big Bang through the formation of the first structures establishes why discovering massive black holes mere hundreds of millions of years after the beginning poses such profound theoretical challenges. The very earliest moments, the Planck epoch from t equals 0 to approximately 10 to the 43 seconds after the Big Bang, remain beyond current physics. At temperatures exceeding 1032 Kelvin and energies approaching the Planck energy near 1019 gigaelectron volts, quantum gravitational effects dominate, and space-time itself likely behaves quantum mechanically rather than classically. No confirmed theory of quantum gravity exists to describe this regime rigorously. Grand unification epoch from 1043 to 1036 seconds saw temperatures around 1027 Kelvin, where the strong, weak, and electromagnetic forces might have unified into a single force. As the universe expanded and cooled, symmetry breaking separated these forces sequentially. The strong force separated first, followed later by separation of electromagnetic and weak forces. Inflationary epoch, potentially occurring between approximately 1036 and 1032 seconds, represents a period of exponential expansion driven by a scalar field called the inflaton. During inflation, the universe expanded by factors exceeding 10 to 96, smoothing initial inhomogeneities and creating the nearly uniform universe observed in the cosmic microwave background. Quantum fluctuations in the inflaton field during inflation became stretched to cosmic scales, seeding the density perturbations that eventually grew into galaxies and large-scale structure. Electroweak symmetry breaking at approximately 10 to 12 seconds and temperatures around 1015 Kelvin separated electromagnetic and weak nuclear forces into distinct interactions. The Higgs mechanism gave masses to W and Z bosons, mediating the weak force while the photon remained massless. This transition created the force structure governing particle physics at accessible energies. Quark-gluon plasma dominated the universe from roughly 10 to 12 to 10 to 6 seconds at temperatures exceeding 1012 Kelvin. Quarks and gluons existed freely rather than confined into hadrons. As temperature dropped below approximately 1012 Kelvin, the quark-hadron transition occurred, confining quarks into protons, neutrons, and other hadrons. This transition fundamentally changed the universe's constituents from quark-gluon plasma to hadronic matter. Big Bang nucleosynthesis occurred from approximately 10 seconds to 20 minutes after the Big Bang, when temperatures ranged from roughly 109 to 108 Kelvin. During this window, nuclear reactions synthesized light elements including deuterium, helium-3, helium-4, and lithium-7 from primordial protons and neutrons. The predicted abundances of these elements match observations remarkably well, providing strong confirmation of Big Bang theory. Approximately 75% of baryonic mass remained hydrogen, single protons, while 25% converted to helium-4, with trace amounts of deuterium, helium-3, and lithium-7. All elements heavier than lithium formed much later in stellar interiors or through stellar explosions, meaning the early universe contained only the lightest elements. This primordial composition affects the formation of the first stars and structures. Matter radiation equality occurred at approximately 47,000 years, when the energy density in matter, dark matter plus baryons, equaled the energy density in radiation, photons plus neutrinos. Before this time, radiation dominated cosmic dynamics and expansion followed radiation, dominated scaling where the scale factor grew as the square root of time. After equality, matter dominated and expansion followed matter-dominated scaling, where scale factor grew as time to the 2/3 power. Recombination epoch at approximately 380,000 years saw electrons combining with nuclei to form neutral atoms as temperature dropped to roughly 3000 Kelvin. Before recombination, free electrons scattered photons efficiently, making the universe opaque to light. After recombination, photons could travel freely through the now transparent neutral gas. These photons form the cosmic microwave background radiation observed today, redshifted from 3000 Kelvin to approximately 2.7 Kelvin by cosmic expansion. The Dark Ages spanned from recombination at 380,000 years to the formation of the first stars at perhaps 100 to 200 million years. During this period, the universe contained only neutral hydrogen and helium gas plus dark matter with no luminous sources. The gas cooled through expansion and slight emission of redshifted Lyman alpha photons. Gravitational instability caused density perturbations to grow, with dark matter halos collapsing first and pulling baryonic gas into their potential wells. The first stars, called population 3 stars, formed when primordial gas clouds reached sufficient density and temperature to ignite hydrogen fusion. Theoretical models predict these stars formed in small dark matter halos with masses around 105 to 106 solar masses at redshifts Z20 to 30 corresponding to cosmic ages of approximately 100 to 200 million years. The lack of heavy elements meant primordial gas cooled less efficiently than metal-enriched gas, likely creating more massive stars than typical in later epochs. Population 3 stars probably had masses ranging from perhaps 10 to several hundred solar masses, much larger than typical stars forming today. These massive stars burned hydrogen rapidly through their short lifetimes of only 2 to 5 million years before ending in supernovae or direct collapse to black holes. The supernovae enriched surrounding gas with heavy elements, enabling subsequent generations of lower mass stars to form. The first black holes formed from population 3 stellar deaths between approximately 100 to 200 million years after the Big Bang. Depending on stellar mass and rotation, these progenitors either exploded as pair instability supernovae leaving no remnant, or collapsed directly to black holes. The expected black hole masses range from perhaps 10 to 100 solar masses for stellar remnants, though recent models suggest some massive stars might collapse to intermediate mass black holes of 100 to 1,000 solar masses under special conditions. Reionization occurred gradually from approximately 150 million to 1 billion years, as ultraviolet radiation from the first stars and quasars ionized the neutral hydrogen-filling intergalactic space. The reionization process was complex and inhomogeneous, with ionized bubbles forming around luminous sources and gradually overlapping until the universe became fully ionized. Observations of the cosmic microwave background and distant quasars constrain reionization history, indicating it completed by redshift Z6 or cosmic age approximately 1 billion years. The first galaxies assembled from mergers of smaller dark matter halos containing first-generation stars. These early galaxies were small by modern standards, containing perhaps millions to tens of millions of solar masses in stars, but they represented the first large-scale structures. Subsequent hierarchical merging built progressively larger galaxies over cosmic time through bottom-up structure formation. The cosmic timeline establishes a definite sequence: Big Bang at T=0, recombination at 380,000 years, first stars at 100 to 200 million years, first stellar mass black holes shortly afterward, and gradual assembly of galaxies and larger structures over subsequent billions of years. This timeline constrains how quickly supermassive black holes could form and grow. For black holes to reach millions to tens of millions of solar masses by cosmic ages of 400 to 500 million years requires extremely rapid growth from stellar mass seeds formed perhaps 100 to 200 million years after the Big Bang. Only 200 to 400 million years of growth time separates seed formation from observed supermassive black holes, a time frame that challenges standard accretion models unless special conditions enable super Eddington growth or alternative formation mechanisms bypass stellar seeds entirely. Understanding the Big Bang timeline reveals why Webb's discoveries of very early supermassive black holes surprise astronomers and create theoretical tensions requiring explanation through either revised formation models or recognition of exotic early universe physics, enabling rapid, massive black hole assembly. Webb's discoveries. The James Webb Space Telescope's unprecedented infrared sensitivity and resolution enable observations of the universe's earliest galaxies and quasars at redshifts exceeding Z-10, corresponding to cosmic ages less than 500 million years. Webb's discoveries throughout 2023 and 2024 revealed numerous massive galaxies and luminous quasars existing far earlier than theoretical models comfortably accommodate, creating what astronomers call the impossible early galaxy problem. Webb's near-infrared camera, NARCam, and mid-infrared instrument, MIRI, observe wavelengths from 0.6 to 28 microns, ideal for detecting high redshift objects whose ultraviolet and optical light has been stretched into infrared wavelengths by cosmic expansion. A galaxy emitting light when the universe was 300 million years old, corresponding to redshift Z15, shows its rest frame ultraviolet emission shifted to near-infrared wavelengths around 2 microns, perfectly matched to Webb's capabilities. The JWST Advanced Deep Extragalactic Survey, JADES, conducted deep imaging and spectroscopy of the Hubble Ultra-Deep Field and surrounding regions, accumulating hundreds of hours of exposure time to detect extremely faint distant objects. JADES discovered galaxies at redshifts exceeding Z-13, including JADES GS-Z13-0 at Z-13.2, corresponding to cosmic age approximately 325 million years. These galaxies appear surprisingly bright and massive given their early formation epochs. The SEERS, Cosmic Evolution Early Release. Science. Survey mapped larger sky areas to shallower depths, discovering numerous galaxies at redshifts Z-9 to 11. Statistical analysis of galaxy counts at high redshifts revealed that bright galaxies appear more numerous than theoretical models predicted, suggesting that galaxy formation proceeded more efficiently in the early universe than standard models assumed. Quasar discoveries provide even more striking evidence for early supermassive black holes. Quasars, among the most luminous objects in the universe, shine through accretion of matter onto supermassive black holes in galaxy centers. The infalling matter heats to millions of degrees, creating radiation across wavelengths from radio through X-rays. The extreme luminosity makes quasars detectable across cosmic distances, despite forming around black holes that, while massive, occupy tiny volumes. Webb observations in coordination with ground-based surveys and Chandra X-ray observatory measurements identified several quasars at redshifts Z-10. The most distant confirmed quasar, UHZ1, shows redshift Z-10.1, corresponding to cosmic age approximately 470 million years. Spectroscopic measurements revealed broad emission lines from hydrogen, carbon, and magnesium moving at velocities exceeding 1,000 kilometers per second, characteristic signatures of gas orbiting close to massive black holes. Analysis of UHZ1's spectrum and luminosity indicates the central black hole contains approximately 40 million solar masses. This mass estimate comes from multiple independent methods, including the width of broad emission lines, which relates to orbital velocity and hence black hole mass, through the virial theorem, and the bolometric luminosity, which scales with black hole mass through accretion efficiency relationships. The existence of a 40 million solar mass black hole at redshift z(10)1 creates immediate tension with standard formation models. If this black hole formed from a stellar mass seed of 100 solar masses at redshift z(20), cosmic age 180 million years, only 290 million years elapsed for growth. Eddington limited accretion with 10% radiative efficiency gives E-folding time approximately 45 million years. Growing from 100 to 40 million solar masses requires ln 40,000, 1,100, or just ln 2.718, 6.0 E-folding times, or approximately 270 million years, just barely sufficient if accretion proceeded continuously at the Eddington limit. However, continuous Eddington limited accretion appears unlikely. Black holes must find sufficient gas to accrete, requiring either smooth cold flows delivering gas efficiently, or galaxy mergers triggering inflows. Feedback from the accreting black hole through radiation and winds heats surrounding gas, potentially halting accretion for periods. Realistic growth histories likely involve intermittent accretion with duty cycles well below 100%, extending required growth time substantially. Additional high redshift quasars discovered by Webb and other observatories show similar tensions. J0313 1806 at redshift z(7.64), cosmic age 670 million years, contains a 1.6 billion solar mass black hole, far more massive than the z(10)1 example, but also having more time for growth. Euless J1342 plus 0928 at z(754) shows a 780 million solar mass black hole. The pattern reveals that even by cosmic ages of 600 to 700 million years, billion solar mass black holes had assembled. The galaxy's stellar masses surrounding early quasars add to the puzzle. Observations reveal that z(10+ quasars reside in galaxies containing hundreds of millions to billions of solar masses in stars. Standard models assume black hole mass correlates with host galaxy bulge mass through the MBH-M-bulge relationship observed locally. Early quasars appear to follow or even exceed this relationship, indicating both the black holes and their host galaxies assembled massive structures remarkably early. Statistical analysis of high redshift quasar counts tests whether rare massive black holes form in the most extreme density peaks in the early universe, as hierarchical structure formation models predict. The observed quasar density at Z6 appears consistent with extrapolations from lower redshifts, assuming the brightest quasars trace rare massive dark matter halos. However, the most luminous quasars at Z.7 begin showing numbers slightly exceeding model predictions, hinting that either quasar lifetimes are longer or black hole formation is more efficient than assumed. Gravitational lensing by foreground galaxies magnifies some high redshift sources, enabling detection of otherwise invisible objects. Webb observations identified several lensed quasars and galaxies at Z10 with magnification factors of 2 to 30 times brightening. These lensed sources allow detailed spectroscopy, revealing chemical compositions, star formation rates, and black hole properties for objects that would remain too faint for study without lensing assistance. The chemical abundances in high redshift quasar spectra surprisingly show substantial heavy element enrichment despite the young ages. Emission lines from carbon, nitrogen, oxygen, and even heavier elements appear with strengths suggesting metallicities reaching 1 to 3 times solar values in quasar broadline regions. Such enrichment requires multiple generations of stellar evolution cycling material through stars, supernovae, and chemical mixing, processes demanding hundreds of millions of years. Yet the universe's age at these redshifts provides only 400 to 600 million years since the Big Bang, with perhaps 300 to 500 million years available for stellar evolution if the first stars formed around 100 to 200 million years. The metallicity levels suggest remarkably efficient chemical evolution, or alternatively, that the broad line regions sample gas that evolved in isolated overdense regions for longer times than global average. Dust emission detected in mid-infrared observations of Z6 quasars indicates substantial dust masses reaching millions of solar masses. Dust formation requires heavy elements produced in stellar evolution, and building such dust masses through supernovae and stellar winds requires considerable time and stellar populations. The presence of so much dust so early again points toward rapid stellar evolution cycles. The combination of massive black holes, substantial stellar masses, high metallicities, and significant dust at redshifts, Z and 10, challenges the idea that structure formation proceeded gradually through hierarchical merging of progressively larger halos. Instead, the observations suggest that certain rare regions of the early universe assembled massive structures extremely rapidly through processes potentially involving rapid gas inflows, intense starbursts, and efficient black hole feeding. Understanding Webb's discoveries establishes that multiple lines of evidence, quasar masses, host galaxy properties, chemical abundances, and dust content all point toward unexpectedly advanced evolution at cosmic ages of 400 to 600 million years. The challenge becomes explaining how all this structure assembled in such limited time, given the constraints of the Big Bang timeline. Black hole formation. Supermassive black holes form through multiple pathways operating across cosmic history, from stellar remnants growing through accretion and mergers to direct collapse of massive gas clouds bypassing stellar evolution entirely. Understanding the formation mechanisms and their timescales reveals why early supermassive black holes challenge standard scenarios while pointing toward exotic processes operating in the unique conditions of the very early universe. Stellar evolution provides the most straightforward black hole formation mechanism. Massive stars with initial masses exceeding approximately 20 to 25 solar masses end their lives in core collapse supernovae or direct collapse to black holes. The stellar core, having exhausted nuclear fuel, becomes gravitationally unstable and collapses in less than 1 second to a configuration where electron and neutron degeneracy pressure cannot provide support. The result is a stellar mass black hole typically containing 5 to 50 solar masses. Population 3 stars, the first generation formed from primordial hydrogen and helium, likely produced more massive black holes than typical stellar evolution today. Theoretical models predict population 3 stars reached masses from tens to perhaps several hundred solar masses due to the lack of heavy elements that would otherwise enable efficient cooling and fragmentation of gas clouds into smaller clumps. More massive stars leave more massive remnants when accounting for mass loss during evolution. However, the most massive population 3 stars might not leave black hole remnants at all. Stars with initial masses from approximately 140 to 260 solar masses experience pair instability supernovae, where gamma-ray photons in the core create electron-positron pairs, reducing pressure support and triggering catastrophic collapse. The resulting explosion completely disrupts the star, leaving no remnant. Only stars below approximately 140 solar masses or above approximately 260 solar masses leave black holes. For stars exceeding roughly 260 solar masses, collapse proceeds to black holes without explosive disruption. These might create black holes of 150 to 300 solar masses or potentially more, though mass loss through stellar winds during the star's lifetime reduces the final remnant mass substantially. Population 3 stars in this regime could plausibly seed supermassive black hole formation with intermediate mass black holes exceeding 100 solar masses. The direct collapse scenario bypasses stellar evolution entirely by collapsing massive gas clouds directly to black holes. Under specific conditions where gas cooling remains inefficient, primordial gas clouds with masses around 104 to 105 solar masses might collapse without fragmenting into stars. The cloud maintains high temperature through gravitational heating, with virial temperature exceeding 104 Kelvin, suppressing fragmentation. The collapse proceeds on dynamical timescales of roughly 100,000 years, creating a supermassive star that quickly becomes unstable and collapses to a black hole. Direct collapse black holes could contain 104 to 105 solar masses immediately upon formation, providing much larger seeds than stellar remnants. Starting from 105 solar masses rather than 100 solar masses reduces the number of e-folding times required to reach 107 solar masses from approximately 12 to roughly 4.6, cutting required growth time from 540 million years to about 210 million years at Eddington limited accretion. The conditions enabling direct collapse appear rare, requiring suppression of molecular hydrogen formation that would otherwise cool the gas efficiently. Lyman-Werner radiation from nearby star-forming regions can photodissociate H2 molecules faster than they form, maintaining gas at temperatures too high for fragmentation. Alternatively, strong streaming velocities between dark matter and baryons in the very early universe might prevent gas from collecting efficiently, delaying star formation until halos become massive enough for direct collapse. Primordial black holes represent an exotic formation mechanism potentially operating in the very early universe before stellar formation began. Quantum fluctuations during cosmic inflation created density perturbations that seeded cosmic structure formation. If certain fluctuations exceeded critical density thresholds, they could collapse to black holes immediately after re-entering the cosmic horizon during radiation-dominated expansion. The mass spectrum of primordial black holes depends on details of the inflation potential and the perturbation spectrum it generates. Different models predict primordial black holes spanning masses from subgram, which would have evaporated via Hawking radiation by now, to thousands of solar masses. If substantial fractions of primordial black holes formed with masses around 1 to 1,000 solar masses, they could seed supermassive black hole formation earlier than stellar evolution allows. Current observational constraints from gravitational microlensing, cosmic microwave background distortions, and gravitational wave backgrounds limit the fraction of dark matter that could consist of primordial black holes in various mass ranges. For masses around 1 to 100 solar masses relevant to black hole seeding, constraints typically limit primordial black hole contributions to less than a few % of total dark matter. While this excludes primordial black holes as dark matter candidates, it permits sufficient numbers to potentially seed some early supermassive black holes. Runaway mergers in dense stellar clusters provide another intermediate mass black hole formation channel. If stellar densities in the cores of the first galaxies reached extreme values exceeding 108 stars per cubic parsec, dynamical timescales become short enough that massive stars can collide and merge before completing their evolution. A sequence of mergers might build very massive stars exceeding 1,000 solar masses that quickly collapse to black holes. However, runaway merger scenarios face challenges including mass loss from stellar winds and the need for extremely dense environments. N-body simulations of young star clusters generally don't produce runaway mergers efficiently unless initial conditions include very compact configurations with central densities far exceeding typical cluster cores. Whether the first galaxies hosted such extreme environments remains uncertain. Black hole mergers driven by galaxy mergers contribute to supermassive black hole growth alongside accretion. When galaxies merge, their central black holes eventually sink to the merged galaxy center through dynamical friction, transferring orbital energy to surrounding stars. Once black holes approach within roughly a parsec, gravitational wave emission shrinks the orbit rapidly, leading to merger within millions of years. The merged black hole contains the sum of both progenitor masses. Binary black hole mergers detected by LIGO and Virgo gravitational wave observatories demonstrate that black hole mergers occur in nature, though the masses involved, typically 5 to 50 solar masses per component, remain far below supermassive scales. Mergers of supermassive black holes produce gravitational waves at frequencies of 10 to 9 to 10·6 Hz, detectable by pulsar timing arrays and planned space-based detectors like LISA, but not by ground-based interferometers. The relative importance of accretion versus mergers for supermassive black hole growth depends on environment and epoch. Simulations suggest that mergers contribute substantially to total growth, perhaps 30 to 50%, with the remainder from accretion. However, mergers alone cannot produce the earliest massive black holes. Initial seeds must exist, and those seeds must grow substantially through accretion before merging contributes significantly. The formation timescale problem emerges clearly when calculating minimum times to build supermassive black holes from stellar seeds. Starting from 100 MEMT tickers at redshift z-20, 180 million years after Big Bang, reaching 40 million M-house requires approximately 6 E-folding times at Eddington limit with 10% efficiency, taking 270 million years. This allows formation by redshift z-10, 470 million years, with negligible margin for intermittent accretion or delayed seed formation. More massive seeds from direct collapse or primordial black holes alleviate this timing tension substantially. A 105 M-catalyst seed requires only 4.6 E-foldings to reach 40 million M-best, achievable in 210 million years. Alternatively, super Eddington accretion with reduced radiative efficiency might enable faster growth from smaller seeds. Understanding which mechanisms operated requires comparing predictions to observations. Growth mechanisms. Black holes grow through two primary mechanisms: accretion of surrounding gas and mergers with other black holes. Understanding the physics governing these processes and the timescales they require reveals both the standard expectations and the exotic scenarios needed to explain the earliest supermassive black holes observed by Webb. Gas accretion onto black holes releases gravitational potential energy as infalling material spirals inward through an accretion disk, friction heating the gas to temperatures of millions to billions of degrees depending on black hole mass and accretion rate. The resulting radiation spans wavelengths from radio through X-rays and gamma rays, with the spectral energy distribution determined by disk temperature profile and geometry. The Eddington luminosity LLED 4PGM MPC SLT represents the maximum luminosity where radiation pressure on electrons exactly balances gravitational attraction on protons, assuming spherical symmetry and Thomson scattering. For a solar mass black hole, LLED and 1.3x 1031 watts. The Eddington luminosity scales linearly with mass, so a million solar mass black hole has LED 1.3x 1037 watts. The Eddington accretion rate follows from dividing Eddington luminosity by radiative efficiency, A, the fraction of rest mass energy radiated. For thin accretion disks around non-rotating black holes, radiative efficiency reaches approximately E 0.06 to 0.1 depending on inner disk radius. Using E, 0.1 gives M-ED, or M-L-ED, E C2, 1.4 C10 8 M year. A 100M black hole accreting at the Eddington rate accumulates approximately 1.4x 10 to 6 M-pennies per year. The mass growth follows exponential increase dm dt 100m or house 1e m ed if accretion proceeds continuously at Eddington limit. The E-folding time for mass to increase by factor E 2.718 equals T-fold m aft E C2 LEDM ast E C2 ST 4PG MPC 0.45 billion years. X A 0.1 for typical radiative efficiency. To average 0.1, the E-folding time reaches approximately 45 million years. Growing from 100M to 17M requires LN 107-102, 11.5 E-folding times, or approximately 520 million years. Growing to 40 million M requires about 6 E-foldings, or 270 million years. These timescales create tension with observations of massive black holes at Z10 when the universe was only 470 million years old. If black hole seeds formed at Z20, 180 million years, only 290 million years elapsed, sufficient for continuous Eddington accretion to produce 40 million M-boys from stellar seeds, but with negligible margin for delays or intermittent accretion. Super Eddington accretion provides one solution by exceeding the Eddington limit through geometric effects or modified physics. If radiation escapes preferentially along polar directions while equatorial accretion continues relatively unimpeded, the effective luminosity in the equatorial plane can remain sub-Eddington even while total luminosity exceeds L-Ed. This allows accretion rates m-Ed while maintaining inflow. Slim disk models for super Eddington accretion show that radiation becomes trapped in dense, optically thick flows, advecting inward with the accreting gas, rather than escaping promptly. This reduces radiative efficiency substantially below standard thin disk values, allowing higher accretion rates for given luminosity. The reduced efficiency paradoxically enables faster mass growth because less accreted mass converts to escaping radiation. For super Eddington accretion at rates m10 to 100 times m-Ed, radiative efficiency might drop to E001 to 0.01 rather than 0.1. The E-folding time becomes T-fold E m-Ed x 45 million years for m cubed to 10 and A001. The E-folding time drops to approximately 4.5 million years, 10 times faster than Eddington limited growth. This would allow growing from 100 mish to 40 million TMs in only 27 million years, rather than 270 million years, easily accommodating observed early massive black holes. However, super Eddington accretion requires special conditions delivering gas at extreme rates. The black hole must reside in an environment providing dense gas inflows exceeding m-Ed. In the early universe, several scenarios might enable such conditions. Cold accretion flows delivering gas directly from the cosmic web into galaxy centers. Without shock heating, could maintain high density and low temperature. The gas would settle into a disk and accrete rapidly before feedback heats and disperses it. Major galaxy mergers funneling gas toward central black holes through gravitational torques remove angular momentum efficiently. Simulations show mergers can trigger accretion rate increases by factors of 10 to 100 for brief periods of a few million to tens of millions of years. Compact nuclear starbursts forming stars at extreme rates of hundreds to thousands of solar masses per year create dense environments where supernova feedback traps gas rather than expelling it. The high pressure confines gas near the black hole, enabling sustained high accretion rates. Counter-rotating gas flows cancelling angular momentum, where gas streams from different directions collide near the black hole. The collision dissipates angular momentum through shocks, allowing gas to fall inward at super Eddington rates. Observational evidence for super Eddington accretion comes from ultra-luminous X-ray sources, ULXs, in nearby galaxies, showing X-ray luminosities exceeding 1039 watts, above the Eddington limit for stellar mass black holes. Detailed observations reveal that some ULXs contain stellar mass black holes accreting at 10 to 100 times Eddington rates, confirming super Eddington accretion occurs in nature. Chaotic accretion models propose that early black hole feeding proceeds through stochastic episodes, alternating between high and low accretion rates. During peaks driven by mergers or cold flows, accretion might reach super Eddington levels briefly. Between episodes, accretion drops to sub-Eddington or ceases entirely while feedback clears gas. Averaging over many episodes produces net growth rates potentially exceeding steady Eddington accretion. The duty cycle, the fraction of time spent accreting, critically affects long-term growth. Even if instantaneous accretion rates reach 10 ed during active phases, a duty cycle of only 10% reduces time-averaged growth to MED. Producing rapid growth requires not just high peak accretion rates, but also sustained high duty cycles, maintaining feeding over substantial fractions of cosmic time. Feedback from black hole accretion through radiation pressure, winds, and jets heats surrounding gas and can halt or reduce accretion by raising gas temperature and driving outflows. The momentum and energy injected by an accreting black hole scale with luminosity, creating self-regulation where accretion rate adjusts to balance inflow and feedback. Breaking this self-regulation to achieve sustained super Eddington growth requires special conditions suppressing feedback efficiency. Magnetic fields threading accretion disks launch winds and jets, carrying away mass, energy, and angular momentum. The mass loss rate in winds might equal or exceed the accretion rate onto the black hole, reducing effective growth despite high inflow rates. Configurations minimizing wind mass loss while maximizing accretion enhance black hole growth efficiency. Torques from non-axis symmetric gravitational potentials including bars, spiral arms, and triaxial halos transport angular momentum outward through gas, enabling inward mass flow. The efficiency of angular momentum transport determines accretion rate for given gas supply. Environments maximizing torque efficiency enable higher accretion rates, reaching or exceeding Eddington limits. Mergers between black holes contribute to mass growth alongside accretion. Binary black holes form when galaxies merge, bringing their central black holes into the merged galaxy center. Dynamical friction against surrounding stars and gas causes the black holes to sink toward the center and eventually form a bound binary with separation, shrinking to roughly a parsec through continued dynamical friction. The final parsec problem arises because dynamical friction becomes inefficient once the binary hardens to separations below approximately 1 parsec. Further shrinkage requires either continued gas-driven migration, interactions with a surrounding dense stellar cusp, or gravitational wave emission. At separations below roughly 0.01 parsecs, gravitational radiation dominates, and the binary coalesces within millions of years. The merger rate depends on galaxy merger rate and binary evolution timescales. In the early universe, galaxy merger rates were higher than today due to smaller galaxy separations and higher densities. However, whether mergers significantly boost black hole masses at the very earliest times depends on whether sufficiently massive black holes existed to merge. Starting from stellar mass seeds, mergers likely contribute little initially, becoming important only after accretion builds substantial masses. Understanding growth mechanisms reveals that standard Eddington limited accretion from stellar seeds struggles to produce the earliest massive black holes unless accretion begins very early and proceeds nearly continuously. Super Eddington accretion, massive seeds, or both appear necessary to accommodate observations within the Big Bang timeline. Alternative explanations, resolving the tension between observed early supermassive black holes and theoretical growth timescales, requires considering alternative scenarios beyond standard stellar seed Eddington limited accretion. Multiple possibilities exist, each involving different physics and making distinct predictions testable through observations. Understanding these alternatives reveals the richness of black hole formation pathways and highlights current uncertainties in early universe physics. Direct collapse black holes forming from massive gas clouds provide substantially larger seed masses than stellar evolution, potentially reaching 104 to 105 solar masses immediately upon formation. This scenario requires preventing fragmentation of collapsing gas clouds into stars, maintaining temperatures above roughly 10,000 Kelvin, where atomic hydrogen cooling dominates, but molecular hydrogen cooling remains inefficient. The conditions enabling direct collapse appear rare and specific. Lyman-Werner radiation in the wavelength range 912 to 1108 angstroms, photodissociates, molecular hydrogen, H2, without ionizing atomic hydrogen. Sufficient Lyman-Werner background flux can destroy H2 faster than it forms through chemical reactions, suppressing H2 cooling and preventing fragmentation. The required flux levels reach approximately 100 to 1,000 times typical stellar backgrounds, demanding nearby intense star-forming regions or quasars. Simulations of direct collapse scenarios show that primordial gas halos with masses around 107 to 108 solar masses exposed to strong Lyman-Werner radiation can undergo rapid isothermal collapse without fragmenting. The collapsing cloud maintains virial temperature T via 10,000 Kelvin through gravitational heating balancing atomic cooling. Within approximately 100,000 years, a supermassive star forms with mass 104 to 105 m°. These supermassive stars quickly become unstable. Stellar structure calculations indicate they cannot reach hydrostatic equilibrium, but instead undergo general relativistic instability and collapse to black holes within roughly 1 million years of formation. The rapid collapse leaves black holes containing most of the progenitor mass, creating 104 to 105 m° seeds without requiring stellar evolution timescales. Starting from 105 m° seeds dramatically reduces required growth. Reaching 40 million m² requires only 4.6 e-folding times, rather than 12, achievable in approximately 210 million years at Eddington limited accretion. Even accounting for intermittent feeding, with 50% duty cycle, growth remains feasible within 400 to 500 million years available in the early universe. However, direct collapse may be self-limiting. The intense radiation from forming supermassive stars or early black hole accretion might destroy nearby Lyman-Werner sources or ionize surrounding gas, preventing additional direct collapse events. The abundance of direct collapse black holes depends on how efficiently these regulatory mechanisms operate, which remains uncertain. Primordial black holes created in the very early universe from quantum fluctuations during inflation provide another exotic seed source. If density perturbations occasionally exceeded critical thresholds, regions could collapse to black holes immediately upon re-entering the cosmic horizon during radiation domination. The mass spectrum depends on inflation potential and perturbation amplitude, allowing black holes spanning orders of magnitude. For primordial black holes to seed supermassive black holes, they must have masses around 1 to 1,000 m³ and avoid overproducing dark matter. Current constraints from gravitational microlensing and cosmic microwave background distortions limit primordial black hole contributions to dark matter to below a few % in this mass range. However, even small fractions could produce sufficient seeds if primordial black holes preferentially sink to galaxy centers where they accrete efficiently. Simulations show that primordial black holes initially distributed throughout dark matter, halos would gradually sink toward halo centers through dynamical friction, collecting in dense nuclear regions where gas densities peak. Multiple primordial black holes in a single halo might merge, building intermediate mass seeds exceeding initial primordial masses. These enhanced seeds then accrete gas, similarly to direct collapse black holes. Modified gravity theories that strengthen gravitational attraction on cosmological scales might accelerate structure formation and black hole growth. Some alternatives to general relativity predict enhanced clustering of matter in the early universe, increasing density contrasts and potentially enabling earlier or more efficient black hole formation. However, these theories face stringent constraints from solar system tests, gravitational wave observations, and cosmic structure formation measurements. Revisions to the Big Bang timeline itself represent the most radical alternative. If the universe is actually older than 13.8 billion years, more time becomes available for structure formation. However, cosmic microwave background observations combined with Big Bang nuclear synthesis abundances, supernova distances, and baryon acoustic oscillations all consistently indicate 13.8 billion year age to high precision. Substantial revisions appear, ruled out by multiple independent measurements. Alternatively, if Ryanization occurred earlier than standard models assume, the first stars formed earlier, providing more time for seed formation and growth. However, observations of the cosmic microwave background polarization constrain Ryanization history, indicating substantial neutral hydrogen existed beyond redshift Z6, limiting how early stars could form. Marginal shifts of perhaps 50 to 100 million years appear possible but insufficient to resolve the massive black hole problem. Local variations in cosmic conditions might enable certain regions to form structures earlier than the global average. If early supermassive black holes formed in rare, overdense regions that collapsed earlier than typical, they could have begun growing before the universe's mean age would suggest. These rare peaks in the primordial density field could be older in terms of gravitational evolution than their cosmic age indicates. However, this merely shifts the question: why do we observe so many early massive black holes if they form only in exceptionally rare peaks? The observed quasar density at high redshifts must match predictions from density field statistics. Current observations suggest early quasars trace rare peaks but not exceptionally rare outliers, consistent with them forming in the tail of the density distribution but not in impossibly unlikely regions. Combined scenarios involving multiple mechanisms likely provide realistic explanations. Perhaps some black holes form from direct collapse, creating massive seeds, while others grow from stellar remnants through super-Eddington accretion, and rare primordial black holes contribute in certain halos. The diversity of formation pathways creates a population spanning wide ranges in properties and formation times. Observational tests can distinguish among alternatives: the abundance of intermediate mass black holes, 103 to 104 m, in dwarf galaxies, tests whether direct collapse or primordial black holes contributed significantly. These mechanisms predict more intermediate mass black holes than stellar evolution alone. Correlations between black hole mass and host galaxy properties test whether black holes and galaxies co-evolve through gas processes or form independently through direct collapse. Gravitational wave observations of massive black hole mergers in the early universe would reveal black hole mass functions at high redshifts. If direct collapse dominates, the characteristic mass scale should peak around 104 to 105 m-acres. If primordial black holes contribute, a different mass distribution emerges. The LISA space-based gravitational wave observatory planned for the 2030s will detect mergers of 103 to 106 m-baus black holes across cosmic time. Chemical abundance patterns in early galaxies constrain formation scenarios through the enrichment history. Direct collapse black holes form without stellar evolution, producing no heavy elements. Stellar-seeded growth enriches surrounding gas through supernovae. Measuring metallicities in gas around early black holes reveals whether stellar evolution preceded black hole formation or whether direct collapse contributed. X-ray and infrared observations of black hole accretion signatures at high redshifts will build census data on early black hole populations. Webb's spectroscopic capabilities enable measuring black hole masses from emission line widths for hundreds of high redshift quasars, mapping mass distributions versus cosmic time, and testing whether masses evolve as theoretical models predict. Understanding alternative explanations reveals that standard stellar seed scenarios likely cannot fully explain the earliest massive black holes, requiring contributions from direct collapse, super-Eddington accretion, or other exotic channels operating efficiently in the unique conditions of the very early universe. Observational challenges. Measuring black hole masses, host galaxy properties, and formation epochs at redshifts Z10 pushes observational capabilities to their limits. Understanding the techniques astronomers use to characterize these distant objects and the uncertainties affecting measurements reveals both the robustness of the early supermassive black hole problem and remaining questions requiring future observations. Spectroscopic observations provide the primary tool for measuring black hole masses through the virial method. Broad emission lines from hydrogen, carbon, magnesium, and other elements show widths of thousands of kilometers per second, reflecting orbital velocities of gas clouds close to the black hole. The line width combined with emission region size determines black hole mass through the virial theorem relating kinetic energy to gravitational potential energy. The virial mass estimator takes the form MBHFX RBLRX dV2 G, where RBLR represents the broad line region radius, dV the velocity dispersion measured from line width, and F a geometric factor of order unity depending on cloud distribution and orientation. The challenge lies in determining RBLR, which cannot be resolved directly at cosmological distances. Reverberation mapping measures RBLR by observing time delays between continuum emission from the accretion disk and responding emission line fluxes. Light travel time from disk to broadline region creates measurable delays ranging from days to months, depending on black hole mass. For nearby active galaxies, extensive monitoring reveals RBLR through cross-correlation analysis between continuum and line light curves. However, reverberation mapping requires monitoring over timescales comparable to light travel times, which for the most massive black holes reach months to years in the rest frame. At redshift Z-10, time dilation stretches rest frame months into observed frame years, making direct reverberation measurements impractical for the earliest supermassive black holes with current observational capabilities. Instead, astronomers used the radius-luminosity relationship empirically calibrated from reverberation mapping studies of lower redshift active galactic nuclei. The relationship RBLR-ELIA with A0.5 allows estimating RBLR from observed luminosity. Combined with line width measurements, this yields virial mass estimates for distant quasars where direct reverberation mapping remains impossible. Uncertainties in this method include scatter in the RBLR-L relationship, roughly 0.4 dex, or factor of 2.5, possible evolution of the relationship with redshift, orientation effects if disk geometry changes with black hole properties, and contamination from narrow emission lines that must be separated from broadline components. Systematic uncertainties reach factors of 2 to 3, meaning reported black hole masses might be overestimated or underestimated by substantial amounts. Photometric redshifts estimated from broadband colors provide initial redshift estimates for faint, high Z candidates detected in imaging surveys. Machine learning algorithms trained on spectroscopic samples predict redshifts from the shape of the spectral energy distribution across multiple filters. Photometric redshifts achieve accuracy DST-1 pleased 0.05 to 0.15 for typical galaxies. However, high redshift objects can suffer from catastrophic outliers where photometric redshifts drastically misestimate true redshift. Emission lines moving in and out of filters as redshift varies create degeneracies. A Lyman alpha emission line at ZT-7.5 looks similar to a OSTI emission line at ZT channel 1.4 in certain filter combinations. Spectroscopic confirmation becomes essential to verify candidate identifications. Webb's NIR-SPEC multi-object spectrograph obtains spectra of hundreds of galaxies simultaneously using programmable microshutter arrays. This enables efficient spectroscopic surveys building large samples at high redshifts. Observations target emission lines including Lyman alpha, rest wavelength 1216.0, CIV 1549.0, and CT 19090, redshifted into near-infrared wavelengths for ZDAR6 sources. Spectroscopic confirmations for Z10 candidates often rely on detecting just one or two emission lines. Secure identification requires multiple lines confirming consistent redshift or characteristic line ratios identifying specific atomic transitions. Single-line detections carry higher uncertainty. An apparent Lyman alpha line might actually represent OII, or another line at different redshift. The cosmic microwave background creates an effective ceiling on observations at wavelengths longer than roughly 30 microns for ground-based and space-based infrared telescopes. Thermal emission from the CMB at 2.7 Kelvin outshines faint, high redshift sources at far infrared wavelengths, limiting observations of dust emission and rest frame infrared spectral features for the most distant objects. Gravitational lensing by foreground galaxies magnifies background high redshift sources, brightening them by factors of 2 to 30 or more in favorable configurations. Strongly lensed sources produce multiple images or extended arcs surrounding foreground lenses. Detailed lens modeling determines magnification factors, allowing reconstruction of intrinsic source properties from observed magnified values. Searching for lensed high redshift sources involves identifying candidates showing characteristic arc morphologies or multiple images near foreground galaxies or clusters. Spectroscopic follow-up confirms whether candidate arcs represent lensed background sources rather than tidal features or other phenomena. Once confirmed, lensing provides magnification enabling detailed study of otherwise inaccessible objects. However, lensing introduces complications including differential magnification, where different parts of extended sources magnify differently, possible contamination from foreground lens light, and uncertainties in lens mass models affecting magnification estimates. Systematic uncertainties from lensing reach 20 to 50% even for well-modeled cases. Stellar population modeling infers galaxy properties including stellar mass, age, star formation rate, and dust content from observed spectral energy distributions. The models fit combinations of stellar populations with different ages and metallicities to reproduce observed fluxes across multiple filters. Degeneracies between age, metallicity, and dust extinction create substantial uncertainties. For high redshift galaxies, rest frame ultraviolet and optical wavelengths shift into observed frame, near-infrared, and mid-infrared bands. Webb's sensitivity in these bands enables stellar population modeling for ZT10 galaxies, constraining stellar masses and ages. Typical uncertainties reach factors of 2 to 3 for stellar mass and up to 0.5 dex in age. Dust emission detected in mid-infrared and sub-millimeter observations reveals dust masses and star formation rates obscured by dust. However, dust emission requires sufficient dust abundance, which may be low in the very early universe before substantial stellar processing of gas. The absence of detected dust emission doesn't necessarily indicate absence of dust, but might reflect sensitivity limits. Chemical abundance measurements from emission line ratios constrain metallicity and enrichment history. Oxygen lines including ORI at 5007 O and OI at 3727 OR combined with hydrogen lines provide metallicity diagnostics. High redshift spectra often show strong OE-HV ratios indicating high ionization and potentially low metallicity, though interpreting line ratios requires understanding ionization conditions. The cosmic variance, the variation in structure abundance due to statistical fluctuations in the underlying density field, affects counts of rare objects like high redshift quasars. Small survey volumes at high redshift mean that finding 1 or 2 quasars might represent sampling rare, overdense regions rather than typical cosmic volumes. Larger surveys covering more sky area reduce cosmic variance uncertainties. Selection effects bias observations toward the most luminous objects detectable at extreme distances. The observed quasar population at ZI10 represents only the brightest examples. Fainter quasars existing at similar redshifts remain invisible, biasing mass estimates toward the upper end of the distribution. Correcting for this selection requires modeling the luminosity function and integrating over undetected populations. Understanding observational challenges establishes that while Webb has definitively detected massive black holes at Z-star 10, uncertainties in mass measurements, redshift determinations, and interpretation mean that quantitative details carry substantial error bars. The qualitative conclusion that surprisingly massive black holes exist very early appears robust, but exact masses and formation times remain uncertain, within factors of 2 to 3. Theoretical puzzles. The early supermassive black holes discovered by Webb create genuine theoretical tensions extending beyond simple timing arguments to encompass black hole galaxy co-evolution, chemical enrichment, reionization contributions, and the nature of the first collapsed structures. Understanding these multifaceted puzzles reveals why early black holes represent broader challenges to structure formation theory rather than isolated anomalies. The MBH-M-bulge relationship observed in the local universe shows that supermassive black hole mass correlates tightly with host galaxy bulge mass, with MBH 0.02x M-bulge. This relationship suggests that black holes and their host galaxies co-evolve through coupled processes involving gas accretion, star formation, and feedback. The tight correlation implies physical connections between black hole growth and galaxy assembly. Early quasars at Z10 appear to follow or even exceed the local MBH-M-bulge relationship. Webb observations reveal host galaxies with stellar masses around 109 to 1010, solar masses surrounding black holes of 107 to 108 MTs, giving mass ratios comparable to or above local values. This suggests that either black hole growth proceeded in lockstep with stellar assembly from the earliest times, or that early black holes formed independently and later merged with growing galaxies. Standard coevolution scenarios propose that gas inflows triggered by mergers or disk instabilities simultaneously fuel central black hole accretion and circumnuclear starbursts. The black hole feedback through radiation pressure, winds, and jets eventually heats and expels gas, quenching both black hole growth and star formation. This self-regulation produces the observed MBH-M-bulge relationship. However, this scenario requires coordinated assembly of both black holes and stellar populations over hundreds of millions of years. For early quasars observed at Z-star 10, this coordination must occur within only 300 to 400 million years of available time. Whether feedback mechanisms regulate efficiently on such short timescales, or whether early systems evolve through different pathways, remains uncertain. Chemical enrichment timescales pose additional puzzles. The high metallicities observed in early quasar spectra, reaching solar values or higher, require substantial stellar processing of primordial gas. Stars form, evolve, explode as supernovae, and enrich surrounding gas with heavy elements through multiple cycles. The enrichment timescale depends on star formation efficiency, stellar initial mass function, and mixing timescales. Simple closed-box chemical evolution models require processing approximately 1 to 3 times the gas mass through stellar evolution to achieve solar metallicity. For a galaxy with 109 MTaus in stars, this demands forming and destroying comparable stellar mass through supernovae over the available 300 to 400 million years. The required star formation rates reach hundreds to thousands of solar masses per year, intense but potentially achievable in compact starbursting systems. However, the timescale problem becomes more acute for specific elements. Carbon and oxygen produced primarily in massive star supernovae can be synthesized relatively quickly, but nitrogen synthesized in intermediate mass stars through CNO cycling requires longer evolutionary timescales. Iron peak elements from type Ia supernovae involving white dwarf progenitors require even more time for white dwarfs to form, accrete, and explode. Yet early quasar spectra show nitrogen and iron lines with strengths suggesting substantial enrichment. Either the chemical evolution proceeded remarkably efficiently with high star formation rates and rapid mixing, or the observed emission regions sample gas that evolved for longer than global average through being locked in dense clumps that collapsed earlier than typical. Dust formation timescales create related constraints. The substantial dust masses detected in early quasars, reaching millions of solar masses, require either efficient dust production in supernova ejecta or grain growth in dense molecular clouds. Both processes take time. Supernova dust yields remain uncertain, but likely range from 0.1 to 1 solar masses per supernova, requiring millions of supernovae to produce observed dust masses. Grain growth through accretion in molecular clouds can amplify dust mass, but requires dense clouds existing for tens to hundreds of millions of years. The rapid appearance of dust suggests either extremely efficient production mechanisms or again that the gas evolved in isolated regions for longer than the global cosmic age might suggest. Reionization contributions from early black holes add another dimension to the puzzle. Quasars emit copious ionizing radiation capable of ionizing surrounding hydrogen, creating expanding ionized bubbles in the intergalactic medium. The volume and topology of ionized regions around early quasars constrain their contribution to cosmic reionization. Observations of the Gunn-Peterson trough in high redshift quasar spectra, complete absorption of Lyman alpha photons blue ward of the Lyman alpha emission line, indicate that the intergalactic medium remains substantially neutral beyond redshift Z6. Individual quasars create ionized bubbles of a few to tens of megaparsecs radius, but global reionization likely completes through contributions from both quasars and star-forming galaxies. If early supermassive black holes are more numerous than expected, their collective ionizing output might have been underestimated in reionization models. The early quasar population could have contributed more to reionization than currently assumed, potentially accelerating the process or creating more complex, inhomogeneous reionization topology. The halo occupation distribution describing how galaxies populate dark matter halos provides another theoretical framework for understanding early structure. Simulations predict that galaxies form in halos above critical masses, with more massive halos hosting more massive galaxies and potentially earlier black hole formation. At redshift Z10, the most massive halos reaching 1011 to 1012 solar masses represent rare peaks in the primordial density field. These rare halos should host the first supermassive black holes. The observed quasar density at Z10 tests whether the assumed halo occupation matches reality. Current observations suggest quasars trace rare but not exceptionally rare peaks roughly consistent with expectations. However, if quasars appear more abundant than halo occupation models predict, this could indicate that black hole formation is more efficient than assumed, or that lower mass halos than expected can host massive black holes. Alternatively, lensing magnification or photometric redshift errors might create false detections inflating apparent abundances. The angular momentum problem affects star and black hole formation from rotating gas clouds. Conservation of angular momentum during cloud collapse creates centrifugal barriers preventing gas from reaching central regions. Efficient angular momentum transport through gravitational torques, magnetic braking, or turbulent viscosity becomes necessary for gas to accrete onto central black holes. Whether angular momentum transport operates efficiently in the early universe remains uncertain. The first collapsing halos might have different angular momentum distributions than later systems, potentially affecting collapse dynamics. Understanding how gas loses angular momentum and settles into accretion disks in early galaxies could reveal why some systems formed massive black holes rapidly, while others did not. Numerical simulations of early galaxy and black hole formation provide theoretical laboratories for testing growth scenarios. State-of-the-art simulations including hydrodynamics, radiative transfer, star formation, feedback, and black hole accretion can follow cosmic structure formation from initial conditions through reionization and beyond. However, simulations face challenges resolving the vast dynamic range from cosmological scales of megaparsecs down to black hole scales of parsecs or less. Subgrid models parameterize unresolved physics including star formation efficiency, supernova feedback, and black hole accretion and feedback. Different subgrid prescriptions produce different predictions for early black hole masses and abundances. Recent simulations incorporating updated black hole seeding models including direct collapse and super Eddington accretion produce earlier massive black holes than previous generations. Some simulations now marginally reproduce observed Z10 black hole masses, suggesting that theoretical models are converging toward observations. However, uncertainties remain large and agreement is not yet robust across different simulation codes. Understanding theoretical puzzles reveals that early supermassive black holes challenge multiple aspects of structure formation theory simultaneously. Resolving these tensions likely requires combined advances in understanding black hole seeding, growth physics, feedback mechanisms, and the statistical properties of the earliest collapsing structures. No pre-Big Bang objects. Despite the provocative title claiming black holes older than the Big Bang itself represents the beginning of time and space-time, making it logically impossible for any object to predate it. Understanding why requires examining what the Big Bang represents, what age means cosmologically, and how the apparent paradox of impossibly early black holes resolves without requiring revisions to the Big Bang framework itself. The Big Bang represents a cosmological model describing the universe's evolution from an initial hot, dense state approximately 13.8 billion years ago. Crucially, the Big Bang is not an explosion in pre-existing space, but rather the beginning of space-time itself. Before the Big Bang, the concepts of before and time lack meaning in the standard cosmological framework. Time itself emerges with the Big Bang. The Big Bang singularity at t = 0 represents a boundary to classical space-time, where physical quantities including density, temperature, and curvature diverge to infinity. Classical general relativity predicts that space-time cannot be extended to times before t = 0 because time itself begins at the singularity. Asking what happened before the Big Bang becomes analogous to asking what lies north of the North Pole. The question contains a category error. However, the classical Big Bang singularity likely represents a breakdown of classical physics rather than a physical reality. Quantum gravitational effects become important at the Planck time, t Planck 1043 seconds, where quantum fluctuations in space-time geometry become comparable to the background curvature. Current physics cannot reliably describe conditions before the Planck time because no complete theory of quantum gravity exists. Some quantum gravity approaches, including loop quantum cosmology, propose that quantum effects replace the classical singularity with a bounce, where the universe undergoes contraction, reaches minimum volume at Planck density, then rebounds into expansion. In these scenarios, time might extend to before t = 0 of the classical Big Bang, with the current expansion phase representing one cycle in a potentially eternal sequence. String theory and M theory permit various pre-Big Bang scenarios including colliding branes, cyclic cosmologies, and emergent time from quantum gravitational states. These speculative models remain far from empirical confirmation, but demonstrate that alternatives to classical Big Bang singularities exist within theoretical physics frameworks. For practical cosmology and structure formation, the relevant question concerns not whether time began absolutely at the Big Bang, but rather when various physical processes occurred relative to the Big Bang epoch. The age of any cosmic object is measured from the Big Bang forward, with the universe's current age providing an absolute upper limit on any structure's age. The claim that black holes are older than the Big Bang represents either misunderstanding or journalistic exaggeration of the actual scientific findings. What observations reveal is that some supermassive black holes appear more massive than theoretical models predict they could grow within the available time since the Big Bang. This creates tension but doesn't imply the black holes literally predate time's beginning. The confusion might arise from comparing black hole ages inferred from their masses to the cosmic time available for growth. If a black hole's mass implies it should be 1 billion years old based on standard growth rates, but it exists when the universe is only 500 million years old, superficial arithmetic might suggest it's older than possible. However, this simply indicates that growth proceeded faster than standard models assume, not that the black hole predates the Big Bang. Age measurements for cosmic objects rely on multiple techniques depending on object type and available data. For galaxies, stellar population synthesis models fit observed spectral energy distributions to infer star formation history and stellar ages. The results indicate when star formation began rather than absolute age since the Big Bang, though the two relate through cosmic chronology. For black holes, age estimation typically relies on inferring formation redshift from growth models. Given an observed mass and assumed growth rate, working backward determines when the seed black hole must have formed to reach current mass. If observed mass exceeds what standard growth models produce in available time, the inferred formation epoch predates what seems possible, creating apparent paradox. However, this paradox resolves by recognizing that growth rate assumptions might be wrong rather than cosmic chronology being wrong. Super Eddington accretion, massive seeds from direct collapse, or other exotic processes enable faster growth than standard models assume. Revising growth physics reconciles observations with cosmic timeline without requiring pre-Big Bang formation. The anthropic principle offers a different perspective on cosmic age and structure formation. If physical constants or initial conditions varied across a multiverse, observers would necessarily find themselves in universes where structure formation succeeded in producing stars, galaxies, and life. Universes where black hole formation failed or proceeded too slowly might exist but lack observers to study them. This anthropic reasoning doesn't explain why our particular universe has the specific properties observed, but it constrains possible values through the requirement that observers exist. Applied to early black holes, anthropic selection might favor universes where black hole formation operates efficiently enough to produce the structures we observe. The multiverse concept permits speculative extensions where different bubble universes within an eternally inflating spacetime have different ages measured from their local Big Bangs. In this framework, some bubble universes could be far older than others, potentially allowing older structures to exist elsewhere in the multiverse landscape. However, this remains pure speculation without observational access to other bubble universes or evidence that the multiverse exists. For practical cosmology describing our observable universe, the Big Bang 13.8 billion years ago represents an absolute temporal origin for all structures we can observe, measure, or interact with. The question of what existence means before the Big Bang connects to deep issues in philosophy of time. Presentist views hold that only the present exists, with past and future being non-existent. Eternalist block universe perspectives treat all of space-time as equally real, with past, present, and future existing as different slices of four-dimensional space-time. In block universe interpretations, the Big Bang represents a boundary to space-time, but all events from Big Bang to far future exist eternally as parts of the complete four-dimensional geometry. In this view, asking whether anything exists before the Big Bang becomes asking whether space-time geometry extends beyond the boundary, which classical general relativity answers negatively. The practical scientific conclusion is unambiguous. Within standard Big Bang cosmology, nothing including black holes can be older than 13.8 billion years measured from the Big Bang. Observations of apparently impossible early black holes indicate not that these objects predate the Big Bang, but rather that our theoretical understanding of black hole formation and growth in the early universe requires revision. The theoretical mechanisms capable of resolving the tension include direct collapse black holes providing massive seeds, super Eddington accretion enabling rapid growth, primordial black holes contributing to seed populations, or combinations of these processes. All operate after the Big Bang within standard cosmic chronology, producing faster structure formation than previous models anticipated without requiring pre-Big Bang physics. Future observations will test these mechanisms by measuring black hole mass functions at various redshifts, constraining seed formation channels through intermediate mass black hole populations, and determining growth rates through quasar duty cycles and accretion signatures. These observations will either confirm that exotic but physically reasonable processes explain early black holes, or potentially reveal tensions requiring more radical revisions. The provocative phrasing "older than the Big Bang" serves journalistic purposes, highlighting the surprising nature of the discoveries, but scientifically the black holes are not and cannot be older than the universe. They represent instead the earliest and most rapidly forming massive structures, pushing theoretical models to their limits while remaining firmly within the Big Bang framework, as the fastest examples of cosmic structure assembly in the universe's history.